Visibility computation is one of the fundamental problems in computer graphics, as it enables a broad spectrum of applications such as shadow mapping, light field rendering, global illumination, or collision detection. A common approach is to determine a potentially visible set, PVS, which contains an approximation of the visible portion of a scene. Computing PVS offline for the region is a common practice to speed up rendering. However, these PVS methods assume restricted occluder or scene structure and are resource-intensive, thus not suitable for real-time applications. Classical from-point methods operate in real time, but they often rely on handcrafted heuristics or are sensitive to the scene complexity, which makes them not the perfect solution for real-time applications. With the ability to learn and model complex mappings, deep learning is increasingly gaining recognition as a new approach to overcome bottlenecks in computer graphics because of its predictable computational cost and speed. Nowadays, neural networks are widely applied in various fields of computer graphics, like neural material, denoising, and global illumination. It is natural to consider the possibility of using a neural network in visibility computation. However, to the best of our knowledge, no existing work addressed this. In this work, we focus on achieving better performance and accuracy with neural network-based visibility computation. The solution to the problem of NeuralPVS is not that straightforward, though. Naively computing all frames is not efficient. The data pattern of different scenes can vary largely, and classical convolutional networks are not very good at processing large 3D volumetric data. To efficiently compute and reuse PVS, we adopt the view cell from the previous work trim region. As shown in the figure, for every PVS computation, we query from a frustum, enclosing all primitives that are potentially visible from the view cell, which allows us to reuse previously computed PVS if the camera is within the view cell. The training dataset must include a wide range of geometric variations to ensure generalization. To achieve this, we utilize synthetic data. As shown here, we randomly place selected objects at varying frequencies and apply random scales and rotations with a consistent distribution across the local object dimensions. To simulate architectural structures such as walls, floors, and ceilings, we scale certain objects significantly along 2 of their 3 dimensions. The camera is randomly placed with a reasonable pose above the floor. The generated dataset is shown on the right side. Classical 3D convolutional networks use dense representation to learn 3D geometry patterns. Dense representations have extremely high memory consumption and lead to slow inference speed. Instead, we use a sparse 3D convolution network and store the data as a sparse tensor, where operations like convolution are faster, more memory efficient, and usually with better performance. To further improve the inference speed, we adopt a 3D volume-preserving interleaving, where some of the elements in the 3D tensor are compressed as extra feature channels to gain speed improvement while keeping the geometric information and doesn't affect performance. Based on the concepts and modules mentioned above, we form our proposed pipeline as follows. A voxelized representation of the input scene is fed into the neural network with interleaving layers and outputs the PVS in voxelized form. The network is trained with pairs consisting of a voxelized scene and the corresponding ground truth PVS in voxelized form, with a given spatial margin around the current camera location. Here, we adopt the weighted dice loss and our proposed repulsive visibility loss to prevent overfitting. Here is the record of a sequence rendered with our method on the Viking village scene. The error pixels are marked in red. For the full metrics, please check the paper. Our main technical contributions can be summarized as follows. We propose a novel neural network for from-region PVS computation, which has significantly improved accuracy and speed compared to existing methods. We explore 3D volumetric interleaving and repulsive visibility loss to enhance the efficiency of the neural network while preserving the accuracy of visibility estimation. We develop a rendering pipeline and application with our proposed method, which demonstrates the effectiveness of our approach through extensive experiments on large scenes, showing that our method outperforms existing state-of-the-art methods in terms of both accuracy and efficiency. Thank you for watching.